Okay, today we're doing more related rates. So we have a cone. So the height of the water level in a cone is changing at a rate of negative 0.2 feet per minute. That makes sense because it's draining. And then the radius is changing at a rate of negative 0.1 feet per minute. So I guess we're like draining it out the bottom, say. What's the rate of change in the volume when the radius is 1 foot and the height is 2? Oops, sorry. We have our picture already. So let's identify some things here. So here's our radius. Pretend that's a straight line as always. And there's our height. We're looking for rate of change in the volume. So we need the volume for a cone. So perhaps you haven't thought about this since you took geometry, but the volume of a cone is 1/3 pi r squared h. It's essentially a third of the volume of a cylinder. So then we'll take the derivative. So we have dv dt equals, I'm going to stick these together. So there's my first part of the product, there's my second part. I always like to put the constants with just one of them. So I'll take the derivative of 1/3 pi r squared, and that'll give us 2/3 pi times r to the first dr dt. So that's f prime times g, so times h, plus the derivative of our second function. Derivative of h is just dh dt times our first function, which was 1/3 pi r squared h. So again, basically, if this was f, this was g, we have f prime times g plus g prime times f. So now we'll put in things that we know. So we're looking for the rate of change in the volume. So dv dt will stay unknown. Instead of 2/3 pi, I'm going to make that 2 pi over 3, just because I can. Radius is 1 foot, so times 1. dr dt is the rate of change of the radius. Radius was changing at a rate of negative 0.1. Height, 2. Plus rate of change of the height, which is dh dt, and that was negative 0.2. Instead of 1/3 pi, let's make it pi over 3. The radius was 1, so r squared is 1 squared, and our height is 2. So if you put all this in your calculator, you end up with dv dt, or the rate of change in the volume, as negative 0.628. Since it's volume, we'll have feet cubed per minute. Shadows and lampposts. Lamppost problems are kind of classic calculus-related rates problems. So we have a 1.8 meter tall man walks away from a 6 meter tall lamppost at a rate of 1.5 meters per second. And the light at the top, this is like a light. We're assuming it kind of looks like a lollipop or something, but that blue, oblong shape is our light. It'll cast a shadow, and we're looking for how far the head of the shadow is moving along the ground. So we make a picture. Okay, that's always our first step. So that's our lamppost. We know our lamppost is 6 meters tall, because we're told. Now we have a 1.8 meter tall man. Let's say this is our man right here. I'm going to redraw him, okay? Let's say this is him. He's happy because who doesn't want to walk away from a lamppost to create a calculus problem? So then if we connect here, we end up with a triangle. Okay, and exactly how it lines up isn't too important. We know that the man now is, I'm going to fill out this in black so we can see our whole triangle too, okay? The height of the man was 1.8 meters. We're looking for the light casts a shadow in front of the man. So this distance here to here, I'm going to call that S for shadow. We also have this distance that the man is away from the lighthouse. Okay, so now what we have is two similar triangles. Okay, we have the big one, and we also have this one. Okay. So now they're going to be similar triangles. It's kind of back to geometry again, okay? Because technically you could do, well, we have the angles are all going to be the same, right? Because we know that this angle down here and the right, and these are both going to be right angles. And so whatever that is, this third angle here and this third angle here, they will be the same. So technically we have angle, 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 and that means the triangles will be similar, okay? Yay, geometry or something. So now we can set up a proportion. So I know that this side of the triangle, so 6, relates to this whole bottom side of the triangle, or leg, so to speak. So 6 is to x plus s. And then this height of this triangle over here is 1.8. And that relates to this leg here of the triangle. So it's sort of upright leg to horizontal leg equals upright leg to horizontal leg. So then we have a proportion. We could leave it like this, I guess, if you want to take a very annoying derivative, but I wouldn't. Let's cross multiply. So we have 6 times s, which is 6s, equals 1.8 times x plus s. So 6s equals 1.8x plus 1.8s. If I subtract my s's on either side, I end up with 4.2s equals 1.8x. So there's our most simplified equation, and now we differentiate. Sorry, it looks like a 5, it's an s. So we have 4.2 ds dt equals 1.8 dx dt. Okay, so now what do we know? Well, this 1.8 meter tall man who was smiling, but now here's that I cut him in half, so maybe he's not so happy anymore, I don't know. But he's walking away from the 6 meter tall lamppost at a rate of 1.5 meters per second. So that means he's here, he's walking along here. So dx dt, the rate at which that distance is changing, is 1.5. Oops, sorry, I wrote it in the wrong spot. So dx dt is 1.5. And we have 1.8, and that will equal 4.2 times ds dt. So solving for ds dt, or the rate of change of the man's shadow, we get 1.8 times 1.5, all divided by 4.2. So ds dt will be 0.6. Okay, so now we try to answer our question. How fast is the head of his shadow moving along the ground? Okay, so this is our man. I'm going to kind of redraw his outline there and his happy face. His shadow, the head of his shadow is going to be down here, right? I don't know that his smile would be in the shadow, but there's his shadow. So how fast is the shadow moving? That's going to be how far is this whole distance changing. And so that whole distance is actually dx dt plus ds dt. And dx dt we already had, that was 1.5. ds dt we just solved for, that was 0.6. So the rate of change of his shadow, or how fast the head of his shadow is moving along the ground, is 2.1, and our units were meters per second.